All right, so we're going to add the harmonic series to call it another test for, well, it's another divergent series. It's the harmonic series. The most general form of it is just 1 over n. We have a series in that shape there. It turns out that if you got a harmonic series, it's divergent. Not a proof or anything, but if I look at some partial sums here, all right, so S1 is just the first term is 1, S2 is the first 2 terms, so that'd be 1 plus a half, which is 1.5. If I look at S3, then it's those 2 plus the third term, 1/3, which is 1.83 repeating. S4 then is those terms plus the 1/4 term, which adds a quarter, which is 2.0833 repeating. So forth and so on down the line. S5 is 2.283 repeating. So it doesn't particularly go anywhere fast, but as far as the sums go. But if you start looking for some things, S11 you pass 3. It's 3.0198. First few terms. So it gets past 3. Well, if you go a little further, S31, this is quite a bit further, but S31 gives you 4.0274, which that is where you pass the 4 threshold. We get past 4. Well, I think you get the idea here. If we just keep going, we can get it to 5, we can get it to 6, we can get it to 7. And so it doesn't prove that it diverges, but it just kind of gives you an idea that we can just keep going and it doesn't ever stop. There's no value that those partial sums will converge to. We'll kind of look at a way here in a little bit where we can actually prove this, but for right now, I just wanted to show you this with the partial sums. Sometimes you get some information off of those partial sums. But anyway, yeah, the harmonic series diverges. And the other point about it, it doesn't matter. I mean, we say it's 1 over n, but 6 over n, that's harmonic series as well, because you could just think of it as factor off the 6, and it's 6 times the harmonic series. So yeah, that still diverges. Whatever number over, if it's a number divided by n, that's the harmonic series, and it diverges. We're related to. Now, this is another good example. We talked about last time the test for divergence. And remember what the test for divergence said? It said if, the TFD, test for divergence, if the limit as n goes to infinity of the a sub n's is not 0, then your series of a sub n diverges. Well, this is a good example because sometimes we want to jump to the conclusion, then, well, if the limit as n goes to infinity, a sub n equals 0, then a sub n must converge. Wrong. And here's a good example, right? Because what's the limit as a sub n, what's the limit of a sub n as n goes to infinity? Well, a sub n is 1 over n. 0. So you got 1 over infinity. It's 0. But we just saw, based on this evidence here, and then more to come, this diverges. So that test for divergence doesn't mean that if your limit of a sub n equals 0, it converges. That's not what that means. It just means it has a chance to converge. Possibly could. If it's not 0, it definitely diverges. If this limit equals 0, it has a chance to converge, but it still may diverge, which this is a good example of one where you got the limit equals 0 and the series itself diverges. So anyway, try to keep that straight. It's a little tricky there, but okay. Now these the next couple here series, I don't call them combinations or whatever. So yeah, let's determine if the series 5 over 2n minus 1 over 3 to the n is convergent. All right, well, from previous discussions, well, I guess we actually have talked about it previously, but hopefully easily enough, if I've got a summation that involves minus or plus, here's what kind of the property I'm using here. All right, so if I've got summation a sub n plus b sub n, or summation a sub n minus b sub n, whatever those things are, I can separate those into two separate summations. I can do the summation a sub n plus the summation b sub n. Summation a sub n here minus the summation b sub n. You see what I'm saying? I can treat them as two different summations. I can do that for addition and subtraction because that's what summation means. It's summation. You're adding up the terms, and so these are obviously added themselves, and so I can certainly split those up. But it also works for subtraction because subtraction is just addition of the negative. So it's really addition and disguise. I can do that. Now, it's a different story. You can't do that for multiplication or division. That's not true. That is not true. You can't do it. So you can only do it in certain cases. But this is one we can't do it. So the moral of the story here is, yeah, I can treat this as two separate series. And then think about, well, what does each of those series do? All right, you recognize this series then? It's not quite in the right form, but couldn't I write that as 5 times 1/2 to the n? Which is, what kind of series is that? Geometric. That's geometric. And R is a half, and that converges, doesn't it? Remember, geometric converges if it's between, R is between -1 and +1. Same thing over here. That's 1/3 to the n, which is geometric. That's the geometric basic shape form. R is 1/3, so that also converges. So if this converges to a number, so does this, doesn't it? I mean, if this converges and this converges, then the difference of those two is going to converge. This is a number, this is a number. Then I'm going to subtract those, I get a number. So determine if that series, that whole series is converted. Yes, it is. Okay. Now, we can do one better. Both of them converge, so the whole thing converges. We can do even one better here because if they're both geometric, I know a formula for the convergence geometric series. It's a over 1 minus r. What's the a here? It's just the first term. N equals 1, so that'd be, what would be the first term? 5 times a half, 5 halves. And then we've already said the R is minus, 1 minus a half there, so it's 5 halves divided by 1 half, which I believe that's 5. Over here, same deal, the first term would be 1/3. And again, my rule of thumb is if I don't write it, it's n equals 1 to infinity. That's where I'm getting those. So the first term here would be 1/3, and then 1 minus 1/3. So it'd be 1/3 divided by 2/3, which that's going to be a half. So it's 5. 5 minus a half, so that's 4 1/2. 5. Okay. So it's convergent, and we can actually determine what it converges to there. All right. What about this one? And yeah, that brings up, makes me think here, because yeah, we'll get all kinds of series and pieces and things. You know, what I'm looking for on these, when we get to the test, is explanation. Tell me why you're saying, don't just say, hey, that converges. Tell me why, okay? That converges, and this is why. All right, so give me some details. All right, so this series very similar. You got a series with 2, so I can think of them separately, separate series. And this here is, well, same as those others. Think of it as 1/5 to the end, so that is geometric, and R is a 5th, so it is convergent. However, what about this one? One we just talked about, wasn't it? What series is that? It's not geometric, it's a harmonic series, yeah. And the harmonic series diverges. So even though this part goes to a number, it actually converges to a number, this one diverges. It keeps getting bigger and bigger, as the case may be. So you've got a number plus infinity, if you will. What do you got? So this series would diverge, right? Yeah, if one part of it diverges, in that instance, the other part also would have to diverge. So that's how that's going to work. All right? Question or concern? Okay.